Okay, today I'm going to show how to solve integration using the method of partial fractions. This is an example, actually is the most simple type of partial fraction that we can have. We have two different factors here that are multiplying, and we said, okay, we can separate it into different fractions that have a value a and b that we don't know exactly what it is right now, but we can figure it out. Basically, if we multiply a by this factor and b by the other one, we will have basically this, and we are saying that the multiplication of this will be the numerator. So the numerator now is 1. If we factorize the x, we say, okay, whatever is with the x, multiplying the x, this sum of a on b will be equal to 0 because we don't have any x in the numerator, right? And everything else will be equal to 1. If we simplify these two equations, we will find that a is the 1/3, negative third, and b is the 1/3. So then we can rewrite the integration as basically two different divisions here, different fractions, and we, by the properties of the integration, we can create the one integral for this part plus the one integral from the other part. Then we can move this outside and have everything that is in the denominator, do the substitution method, and we'll have the logarithm, natural logarithm of the denominator, right? Plus the constant. Another example that we can have is this: whenever we have repetitions of the factors in the denominator, right? In this case, we have a different form. We have 1 should be just a single of the factor. The second one should be the square, the number of factors that we have here, plus the third one that is not related to the one that is repeated. We do exactly the same thing that we have in the example 1. We equal the multiplication of all these factors by the numbers that we have in the top, and we equal that to the numerator. And then if we if we solve the matrix that we have here, we will find that a is 1, b is 2, and c is -3. Same thing, we separated everything in 3 different factors, and we will have that these two are the natural logarithms, and this one is the negative exponent. So we have in a different way plus k. K is the constant. I changed just the letter because we have c here, and I don't want to have any confusion about that. So another example that we have here is this. Okay, what happened in this case? We have the square is basically it is inside of the factor. It's not that the factor is repeated. We have the square inside. So for this one, we have a different way to do the factorization, which is with this term that include an x in the top, a and b, 2 different numbers plus c. Again, we do the multiplication of both like that, and we have to equal this to the numerator, and then separated that in the matrix. If we solve the matrix, we will find that the a, b, and c are equal to 1. So then we will rewrite this as here, 1 multiplying by x and 1 alone here, that is one term, and the other one is here. So how are we going to resolve this? For this one, for this part, we can separate this into different fractions, right? One will be the x, like we have it here, and the other one is the 1, right? Everything with the same denominator. It's just addition of fractions. And the other one is the same. So for this one, we can do the substitution. This is the method that I explained in the previous video. the substitution, we get this substitution u, and du will be 2x, but we don't have the 2 here, we only have the x, the derivative, so we add this 1/2 to the du, and then we will have this function, which is 1/2 of the logarithm, the natural logarithms of the denominator plus k1, right? The second part, okay, this one is direct. We know that we do also substitution here, we will have the natural logarithms, right? Plus another constant. And this one, this is different. For this one, we need to have a substitution, a tangent substitution, and actually I will create another video for that, but this is more or less how it works. We have the tangent substitution of theta. Of course, theta will be the arcotangent of x, right? And the derivative is the secant squared of theta, right? So if we do that substitution here, you know also tangent is sin squared over cosine squared, right? And if we put this below, it will, this one will go away with this one, and this will multiply by 1 too, right? So we will have this Pythagorean trigonometric identity, which is this is equal to 1, remember? So if it's equal to 1, we will basically have only the d theta, which is this one that we have here, and basically the integral of the derivative of theta is theta plus another constant, and we say that theta is the arcotangent of x, so that is why the final solution will be the logarithms of this denominator of the first equation plus the arcotangent of x plus the natural logarithms of the denominator here, right? Plus another constant k. Finally, this is another example that I have here. Okay, this is different of the other ones. Here we have that the denominator is lower degree than the numerator, right? In this case, we can, I mean, most of the cases we have to do the long divisions, right? And see what is the remaining. Or in this particular case, if we get the common factor x of this part, right, we will have x multiplying by this, that is exactly the same of the denominator, plus 1. If we separated this into different fractions, we can get rid of this one too, right, and have only x plus the part with the 1, which is exactly the same. We don't do anything in that side, right? Of course, with this is a squared a polynomial, so a polynomial of second grade, so sometimes we can do also factorization here, that is easy to do it, and then this part that we have here is a perfect candidate for a partial fraction. Now we do the same operation that we did previously here, that we separated into different fractions. We do also the multiplication of the factors by these variables that we don't know what they are, and then we create them the matrix, and we resolve the matrix, and we have basically separated in two different fractions, and then we can show this integral that looks very messy with this clean form of the integral, and then we can just apply the antiderivative of each term.